All right. How's everyone?
Doing pretty well, I suppose. How are you, sir?
Good. Midterm coming along?
Yeah, that's doing pretty good here. Just started 3. I didn't get much sleep last night, so instead of jumping in on that, I decided to do some programming assignments. But yeah, it seems pretty good to go there, I think.
I've looked at it, but I haven't actually started like writing up the solutions, but mentally it's going pretty well.
There are questions. So last time we talked about the low rank approximation, right? The closest rank K matrix to a matrix A. And basically the idea is that you keep K singular values and throw everything else out, and that's how you get the best rank K matrix approximation. This is a really actually important thing in practice because sometimes these singular values are really small. You know, maybe they should be 0, but the computer gives you an error, you know, like a little tiny number just because of some rounding. And so the small singular values bring less information, and you can kind of cut them off, and you won't lose much. There are some pictures in the book. I think there's a picture of a clown. And then I think even in the main cover of the book, there's a picture of a baby. There's 4 pictures. I think those are the low rank approximations. Another, oh, I forgot to share. Am I sharing?
No, I don't
No.
think so.
Oh, okay. I was pointing here, sorry. I was pointing to this last week's lecture, the closest rank K matrix and the singular values. All right, so, and this is what happens when you do that. You basically keep the vectors up to the kth vector, both in the columns here and the row there, and then you keep only K singular values, and you get this low rank approximation. The typical example that I usually give is this one. This is the original image. It's a matrix of pixels. So it's a 359 by 371. Every pixel has a magnitude, I think, between 0 and 255. I think, I'm not sure actually. In any case, you compute the singular value decomposition, and you see they give you the dimensions here. So they are taking the case where U is square and V is square, and sigma has the same shape as the original matrix. So you can also write it like that, order them. And so here it says significant compression of the image is possible if the spectrum of singular value has only a few very strong entries. So let's look at, here they plot the magnitude of the singular values in decreasing order. And you see, yeah, there are some really big singular values. And then they kind of stabilize. And then towards the end, they become small. So he says the spectrum is contained principally in the first 100 to 200 modes. So about between, you know. All right, so here are the low rank approximation. The first one, this is the rank one, right? You just keep one vector, and this is what happened in one singular value. This is the rank one approximation. It's amazing how already you're capturing certain things, right? You're capturing the grid structure. Now, this is with 10 modes. You're starting to see, you know, you need to be able to figure out these numbers. This uses 5% of the storage as you know, instead of keeping the matrix of pixels. Basically, because all you have to keep is the singular 10 singular values and 20 vectors. Right, this is 20, 30, 40, and already with 40, you can read the numbers. 50, 100, 100 is pretty good. 200. All right, questions?
No, that is quite interesting though, because I still have a hard time visualizing an outer product at times in terms of what got distributed where. I mean, this kind of shows it, right?
Yeah, right, especially the first one.
Right, all the information's concentrated in the vectors associated with the largest singular value.
Yeah. Yeah.
I don't know what else, what other insight comes along with that. I'd have to think about that for a second.
Yeah, say that again.
Is there some kind of general rule for like what the cutoff is of like this is a good cutoff, and or like what are quote unquote large values and what's small?
No, unfortunately, I think it's kind of an art to figure out where to cut off things. You know, as we were scrolling along, we were using our human eye, and then, you know, oh, this looks pretty good. Oh, now we can read the numbers. I think those are really hard things to automize. You know, to have a machine decide where to stop. You could have some rule of thumbs, I guess. I mean, you could imagine trying to maybe pick the median of these values, or I don't know. Actually, I'm not sure.
Right, because it would be very application specific, because you'd have multiple considerations to balance making it an art, right? In almost every application, given a sufficient large application, you'd be considering system performance with storage and compute power. But at the same time, you'd be balancing two different perspectives, I would say, maybe between let me approximate this because I don't care about the loss of information. But the flip side of it might be a more defensive programming perspective in which you don't want to introduce even minute false data from the smaller values.
Exactly. Yeah,
and
some of this
perspective would be very application dependent.
Yeah, some of the small values could be spurious due to, you know, computer rounding or something.
Right. You wouldn't want, wouldn't want to miscalculate your space trash colliding.
Say that again?
Oh, I was joking. I was saying, yeah, you wouldn't want to have false data in there and miscalculate your space junk colliding.
Right.
Very true.
Yeah. And then, you know, it also depends on the problem, because sometimes it's very obvious. There's like, you know, as the guy was saying, you know, there are very, very high singular values, and it kind of drops out much more obviously. And then other times it's more, you know, harder to cut. So yeah, it depends. It's amazing to me how much you can do with even just three, you know, three singular values already. A lot of the visualizations in R3 of things, like graph, you know, very, very complicated networks, for instance, come from that, just keeping the first three. So, all right. All right. So we'll get back to this. I mean, this is a big field, but at least we have the fundamental property here.
Before we transition, sir, I just want to throw out there that the lecture 25 isn't posted or listed out there. I wasn't sure if you were waiting until today.
It's not posted on the webpage.
The video is on YouTube, but this posting is not on the webpage.
Oh. Huh. Oh yeah, I forgot to post it. Okay, I'll post it after we are done. Thanks for reminding me. All right, so let's do lecture 26. And so today I want to talk about the pseudo-inverse, sometimes also called Moore-Penrose. I don't think this is the same Penrose that just won the Nobel Prize in Physics. It might be a different Penrose. Pseudo. Okay, so suppose you have a matrix, rectangular matrix. For simplicity, let's assume that we have more rows than columns, and you can handle the other case separately. And also, let me assume that it's full rank, full column rank. All right, so then we know, we've seen that you can have a QR decomposition, or you can have a SVD decomposition. The pseudo-inverse is sometimes denoted with a plus or a dagger. In older texts, they have a dagger. I think more recently, plus has been more common. So it's the following formula. It's A transpose A inverse A trans. Remember, in this case, so the projection onto the image of A was given by A transpose A inverse A transpose, right? So in these notations, it would become like this, A plus. All right, so let's kind of understand where does this come from. Move this, kind of in terms of the QR and the SVD, right? So in terms of the QR, then let's just kind of go through the motions. A plus, pseudo-inverse, is what? Okay, so we need to take R transpose Q transpose QR inverse R transpose Q trans, right? And then this here is the identity. And then R is invertible, right? Because the diagonal elements are positive. So this all simplifies to down to R inverse Q trans. So if you remember, I said that you should think of an analogy with polar coordinates. If you know complex numbers in polar coordinates, if you have a complex number z in the complex plane, you can write it as r e to the I theta. You know this fact?
Yes.
So this is theta, and this is r. And so when you take the inverse, right, it's always good to have this kind of analogies, at least I think. Sorry, I don't know what that. When you take the inverse, what are you going to do? Well, you're going to take, 1 over. But of course, you can write this as r, the magnitude, r inverse of the magnitude is e to the minus I theta. And e to the minus I theta is the conjugate of e to the I theta. So it's very similar to this expression here, where you take the magnitude, in quotation mark r, you invert that, and then the q is like the rotation term, and that you take the conjugate. That makes sense? Just an aside here. All right. So so that was that. Now let's do the SVD interpretation. So, and what did I call it? In terms of all right. So in terms of the SVD, again, let's just plug things in. So we need to do A transpose A. That's V sigma U transpose U sigma V transpose inverse V sigma U transpose. Right? And this is going to be 1. So we get sigma squared. Now, let me assume here that I'm I'm writing A as U sigma V transpose, where this is n by n. This is n by n. And so V is an orthogonal matrix, a fully orthogonal matrix. So it has an inverse, and the inverse is the transpose. So here, when I take this, is going to be V sigma U. Again, this is the identity here. Sigma to the minus 2 times sigma, so that's going to be sigma to the minus 1. All right. So what do we see here? First of all, if you think of V and U as being change of basis, right? A is the following: change your coordinate bases in Rn, do a diagonal multiplication, and then change your coordinates in Rm, right? Roughly speaking. Well, A plus is doing the opposite, is changing things in Rm, doing a multiplications, and then changing coordinates in Rn. So it's going back, from Rm to Rn, which makes sense. And moreover, you can write this in this other notation as basically 1 over sigma j, dj, uj. Right? I kind of like this last one, because if you think of A as the sum as j goes from 1 to r of sigma j, uj, vj transpose, and then you get, for instance, if you want to multiply A and A plus, right? You want to do A plus. Let me use a different number here, a different letter, sigma I. Right, you can kind of see what's going to happen, because when you distribute this, well, you're going to sum over I and j from 1 to r, sigma j over sigma I, uj, vj transpose, vi, ui transpose. But you see, the v's are orthonormal, right? So all of these inner products here are either 0 or 1. Basically, the only thing that survives in the sums are the diagonal elements. And when j equals I, you get 1 here. So you're left with uj, which is the projection onto the image of A. Because the image of A is the span of u1 through ur. I don't know, I somehow am partial to this sigma notation way of writing the singular value decomposition, because you kind of see the vectors, and matrices are a little more opaque, in my view. All right, questions? So, so for instance, let's kind of re-examine the normal equation. We revisit the normal equation, A transpose A X equal A transpose B. And then because we are in the 4-column rank case, we can just invert this. Right? But that's exactly, you know, this is A plus B. That makes sense? So that's why it's called a pseudo-inverse. It's the least square solution of the system. All right, questions? Now we can do the general case too, where you don't have full column rank. So more generally, so in that case, let me write U as U of R, where R is the rank, and then the rest, you know, U tilde, which is the completion, and likewise for V. All right. So in that case, then so this is going to be M by M, n by n. And then sigma will have a block, sigma R block, and then some blocks, some zero blocks. And this will retain the shape. So let's look at the equation ax minus b. So that becomes u sigma transpose x. And I can rewrite this. So let me write v transpose x as, so because I have this block decomposition, right? So it's going to be, so I have VR transpose and V tilde transpose X, right? Or VR transpose X, V tilde X. And let me give a name to this. I'm just going to call this W. It's the rotated X. So then here I can rewrite this as U, and then, you know, because of the block structure of sigma, if you do sigma times W, what you're going to get is something like this. And for B, remember B is a vector in Rm. So I'm going to write it as U U transpose B so that I can factor out U here. And U transpose B also has a block structure. So it's going to be UR transpose B. That makes sense? Just kind of manipulations here with the block structure, so that when I then go and look at the 2 norm squared, I don't care about this this first rotation, you know, this unitary, because 2 norms are invariant and they're orthogonal matrices. So I can simply take the norm of sigma RW minus UR transpose V. Simply take the 2 norm square of this. But, you know, by the Pythagorean theorem, essentially, this is going to be the sum of the 2 norm of this vector plus norm of this. That makes sense?
Yeah.
All right, and now we're trying to minimize by varying x, right? We're trying to minimize this norm by varying x, so we're varying w here. Everything else is fixed. And so that what we want is w to be sigma R inverse of UR transpose. Sigma R is invertible because, you know, it's diagonal R by R with non-zero diagonal entries. All right. Okay, but remember W, W, where was it? Yeah, so W is this thing here. So actually, I didn't want to write it like that. Sorry, I think I made a mistake. I wanted to write it as WZ. I think nothing changes because when you multiply V transpose by sigma, the Z, you know, the Z goes away because, you know, sigma has got all these zeros. I think nothing changes here in what I just did. All right, but so now let's think of X, right? X is going to be V times WZ. So it's VR V tilde. This is just an inner product in the block calculus. It's going to look like that. And W, we know we have an expression for. So by plugging that in, I get VR sigma R inverse UR transpose B plus B tilde of Z. So that's the least square solution. And you know, this is exactly A plus of B. You can recognize that from this expression here, right? You take the VJs from 1 to R, the UJs from 1 to R, and the 1 over sigma Js. That's exactly this expression. So that's A plus B. And then V tilde Z, this is in the kernel. Right, because V, the columns of V are orthonormal. And so, right, so when you, when A is U sigma V transpose, and is that clear then? Let me see. We apply that to V tilde. Yeah, you have to kind of follow through, but yeah, it's gonna turn out that this is in the kernel of A. Right, which makes sense, right? Because we are thinking of, in this case, we don't have full column rank. So the picture is like this. A maps to some higher dimensional space as a certain image. And then B is over here. And the idea is that you project orthogonally down. So this is going to be, you know, A plus of B. And then, but now this actually comes from a whole set of vectors, which is a translation of the kernel, right? So this is going to be A plus B as kernel of A. The kernel always goes through the origin. Now we move it, right? And the claim is that actually even in this general case, the pseudo, you know, the pseudo inverse of B is this representative, the perpendicular one. So there's a whole class here of least square solutions, but the pseudo inverse picks out the one that has least norm. So let's show that. So note X is VR V tilde times this W, which was sigma R inverse UR transpose B Z, right? So let's compute its norm. The norm square is going to be, you know, think of this as V here, right? V again is an orthogonal transformation. It doesn't matter. So really it's going to be the norm square of this. And then by Pythagorean theorem, you can write it like this, right? But certainly this is always greater than sigma R inverse UR transpose B square. And then you can, by orthogonality again, you can put in VR, which is A plus B squared. So that shows that A plus B, out of all the least square solutions, A plus B is the one of least norm. All right, does that make sense? All right, so before we move on, I wanted to do an example of sort of the pseudo-inverse in action. Um, and since we've talked about the Laplacian, I thought, why don't we talk about the pseudo-inverse of the Laplacian as an example in practice? We already mentioned some things about the Laplacian. I'm going to work in the generality of a graph G with some nodes and some edges. The nodes are going to be numbered 1 through n, and the edges are going to be pairs of nodes. So in this case, you know, you could call this a simple graph. And then the Laplacian, you can think of it as D minus A, where A is the adjacency matrix and D is the diagonal matrix of degrees. D is the diagonal degrees. A is the adjacency matrix, meaning that it's either 0 or 1, depending on whether X and Y are neighbors. All right, that's one way of presenting the Laplacian. Another way of presenting the Laplacian is as a sum over the edges of dx minus dy, dx minus dy. Okay. And in this case, we saw, did we see this last time? You can think of this as B transpose B, where B is the gradient matrix. That for every edge, you pick an orientation so that then you can write dy dx. transpose, and you put it like that, right? This is called the gradient. So it's called the gradient matrix because if you give me a function, so it's a, right, it's an E by V matrix. These delta x's, these are delta x here is the indicator of x, of the node x. It's either 0 or 1. So it's a function on the vertices. And it's called the gradient matrix because if you have a function on the vertices, so if you have a vector in RV, then VH is going to be a vector in RE, right, with the appropriate orientation. So some kind of oriented set of edges. And for every edge, you have, you got to multiply. So what happens when you do dy dx transpose H? Well, you just get H of y minus H of x. Now you take the difference of the function at the nodes. You have two nodes, x and y, and you have a function here, H of y, H of x. And the gradient matrix gives you the difference and puts it and assigns it to the edge. Right, so it's kind of like a derivative or a gradient in calculus. All right. Now, B transpose, did I already mention this? I thought I is a divergence. Is akin to the divergence. Did I already mention these things? I feel like
Yes,
I did.
we went through it. We might have spent through part of this towards the end when we talked about it a little bit.
Okay, so B transpose is divergence, meaning that if you have a flow, if F is a flow, so then F, you can think of it as being, a vector in RE with the orientation. And B transpose, kind of goes the other way around. It gives you a function on the nodes. And B transpose F at a node X is exactly the divergence of F sum over the neighbors. This you can verify easily. So I ran out of time, but basically I've set up everything I need to then talk about the pseudo-inverse of the Laplacian next time on Monday.
Okay, cool. Thank you, sir.
All right.
Yeah, everyone have a good weekend.